Hello, everybody, and welcome to our Hydrography, Geophysics, and Geotechnics track today. We've got three speakers for you. We've got Roy Santos, we've got Gareth Wood, and we've got Mark Vardy. First speaker up is going to be Roy Santos. He did his BSc and MSc in Ocean Sciences from Vigo University in Spain, and then a Master's in Geophysics and Geotechnics from Bangor in North Wales, and a Master's in Soil Mechanics from Imperial College in London. Roy joined Guardline in 2006, where he'd been involved in multiple large-scale offshore site investigations around the world, and is currently, well, until a few days ago, was leading the geotechnical consultancy team at Guardline, supervising the foundation design team and providing technical advice to the R&D and site investigation teams. So he's convener of the ISO TC182 working group, reviewing the new ISO standards for cone penetration tests. And he's going to be talking to us on a review and update of standards for seismic cone testing. So over to you, Roy.
Okay, so I'm gonna be discussing the new update of the ISO 19901 that regards marine site investigations. The outline of the presentation covers very briefly the process of developing standard documents, a scope of the update of this particular ISO standard, and in particular in situ testing chapter and the update on application classes. And at the end, I will do a brief summary of the presentations. The marine soil investigation standard was first published in 2014, and since it has been in standard use in our industry, but in 2018 there was a proposal for review of the standard. It was received, many comments has been received. There is a graph here showing the distribution of the comment in reference to the contents of the standard, where you can see that most of the comments were on in situ testing chapter. Other major comments was received on lab testing, reporting, and so that was what triggers this new update. And the working group is currently working towards having a draft standard document for ISO committee approval in 2021. Very briefly, this is the stages straight from the ISO webpage. So there are 6 stages: proposal, preparatory, where the working group is set up to work on a new draft that basically address the current comments. Once the working group creates a draft for committee review, then the committee need to review technically and agree on get a consensus on the and an agreement on the changes performed, and then it's sent as a draft international standard to the central secretariat, where then is distributed to all ISO members, and a vote is taking place for approval. If any technical challenges at that stage, then that draft is sent back to the working group, which will have to address those drafts, those comments, and then send for a second vote. And the final publication stage is no further technical challenges are allowed, only editorial changes. Currently, we've been working 2 years on this, and we are at committee stage and at the very last stages, and towards the end of the year, we hope to have the draft international standard ready for issuing to ISO. In terms of the document covers all the geotechnical site investigation aspects, from objectives, planning and requirements, to the details of how you go about deploying site investigation equipment, the process of drilling, in situ testing, sampling, lab testing, and the reporting. So it's a very complete document covering the whole spectrum. And here I summarize the main chapters, and I color-coded them, trying to classify where the major changes are. As you can see, the chapters highlighted in yellow are the ones where some minor changes has been introduced, while the red ones are those where major changes has been implemented. And I've been part of within the working group. There was subgroups focusing on different chapters. I've been working mainly in the in situ testing chapter, so I will focus this presentation on that. Okay, so chapter 8, in situ testing, covers CPT testing, dissipation tests, full flow penetrometers, and seismic penetration test. And as you can see, in this table, I again use the same color code, and it's clear that the in situ chapter has gone through substantial changes, and the major ones correspond to the CPT chapter and the seismic CPT chapters. In addition, a new annex, which is normative, not informative, has been introduced in order to create a more robust system for calibration and validation of compenetrometers. In terms of why we did these substantial changes, and basically the main driver was the application class. In the current version of the standard, there is a classification of test types based on the accuracy of the measurements, and each of the classes are intended for certain soil types, and there is a series of values of accuracy for tip, sleeve, and pore pressure that make your test being accuracy class 1, 2, or 3. But this approach was a little bit controversial in the sense that was very difficult. Well, the whole thing was linked to soil profile, equipment capability, and compliance of the result. However, we never were 100% sure about what is the true value, and therefore was not so easy to understand, to quantify the uncertainty of each one of those aspects. And the standard in itself wasn't giving very clear guidelines how you go about calculating the uncertainty associated to the results. So we have been working on a slightly different approach, which a more pragmatic approach, we believe, which basically replace application class by 2 stages. The first one is the compenetrometer class. So that is basically focused on the measurement system. Is under lab conditions, we can determine the uncertainty of the measuring system. And then a second stage, which is based on diagnosis while collecting data in the field. There is a series of tools we can use to diagnose that the test conducted provides certain guidelines for quality control of that test, basically. So in the next slide, I will go through the 2 steps. The first, as we were saying, compenetrometer class. So we introduce a series of classes within the measuring system, class 1+, 1, and 2. And we give clear requirements for the calibration in accredited laboratory for each one of the sensors of that cone. In addition, we also have the committee have acknowledged the large influence that temperature has on measurement systems, especially on strain gauges, and that's why we introduced um, two entries, which tells or regulates how the cone will cope with temperature changes, because that can cause large drifts and have big impact on the results. In addition, we have also included bending error, because the load cells are also susceptible to errors due to lateral loading. In terms of how we go about calibrating, in order to ensure that all the manufacturers, all the operators calibrates the cone in the same manner and calculates the uncertainty of the measurement system, we have also created a new normative annex in which it provides a very robust procedure for calibrating cones, and also how to calculate uncertainty. Basically, what we propose is the summation of a series of uncertainty contributors, which are listed here. So you have a summation of 8 of these contributors, and the test include several loads and load cycle, um, rotating the cone in order to provide enough data so that the calculation of uncertainty in the laboratory is meaningful. And here you see the equations, and there is two aspects. One is for the calibration certificate, you need to include the calculation of the 8 components, including the dimension with it, which is a 9th component. And for the conformity statement for cone class, we include all of those paths for the reference force and the dimensional uncertainty. And that's for classification of the cone as class 1, 2, 3, or 1 plus. We also intending to provide an example calibration certificate. So again, to ensure that is every manufacturer or every operator present the same data sets, and everyone in the industry is get used to see the results from a calibration certificate. The second stage in this quality control for cone penetrometer tests is the evaluation in the field. So this happens after the test is conducted, and basically we have defined 3 categories, A, B, and C, and each one of these categories are meant to be used in certain soil profiles, and we basically classify them in accordance to the measured cone resistance, and that's the maximum value measured during a test. So class type A is for soils with less than 2 MPa maximum cone resistance, and from 2 to 60 for type B, and more than 60 type C. And the field checks are based on difference on zero readings or reference readings before and after the test. So those basically give you an indication of if the strain gauges or the cone or the pressure transducers have gone damaged. Generally, the drifts in the sensors before and after the test should tell you how healthy your cone is after conducting a test, and that's what drives this. And the second one is the output stability, which is basically how stable the measurement system is, again, before and after the test. And with that, we are able to give a quantification of the quality of certain tests. Finally, in terms of the Seismic Cpt update, There has been a lot of debate in this chapter within the working group, but we wanted to, and we acknowledge that there is still quite a bit of research to be done in terms of improving the repeatability and the robustness of the seismic CPT results. However, we wanted to tighten a little bit the requirements and making the results more easy to compare between operators and contractors. So we have included a clear requirement about the position and orientation of the source, and as we believe is fundamental to get a very accurate distance between the source and the sensors, and also the orientation of the source, as is paramount to get good shear wave velocities. Um, in terms of, we have also introduced a new requirement for recording of the triggering signal, which allows then to compare the received source to the trigger signal, which give more certainty when it comes to the interpretation. And we also include pre-triggering. Well, it's a requirement to do a pre-triggering before the first arrival, which also allows, for example, to quantify the noise to signal ratio, and again helps with interpretation. In terms of repeatability and accuracy, there is new comments and recommendations provided in the annex, and hopefully this will help the current users of the data and to select the right system for their requirements. And then there is a clear statement about the data and how it should be available. The unfiltered data should be available to users of the data, and also subsequent post-processing methods need to be reported. If any filters has been applied, has to be reported. And finally, we also have put a statement that says that the process, well, the interpretation process also method has to be reported. So what type of methodology has been used for determining the shear wave velocities. And with that, I conclude this brief summary of the presentation. So I briefly reviewed, give an overview of the work is done in the ISO group, showing which chapters include the major changes. As you heard, the in situ testing has come with large, well, the in situ working group have come with a lot of changes for application classes, and also include new clauses for the seismic Cpt. Thank you very much.
Excellent. Thanks very much, Roy. That was really good, really interesting. So our speaker this morning is Mark Vardy. He is now the director of SAND Geophysics. The subject is going to be machine learning for site investigation. Is it actually useful? A little bit of background about Mark. It says he's worked on all manner of offshore projects, from inshore infrastructure developments to large-scale offshore installations with a broad range of clients. He specializes in the development of novel, high-resolution geophysical solutions to marine near-surface problems, and was co-inventor of the 3D chirp seismic system. He's also co-designed a multi-channel seismic streamer and developed two specialist seismic software packages to provide optimum qualitative and quantitative imagery from high-resolution seismic reflection data. In particular, his development of machine learning workflows to predict geotechnical properties from seismic reflection data has garnered significant interest in the marine site survey sector. So over to you, Mark. Thanks very much.
Hopefully everybody can see that okay. So yeah, thank you for joining into this slightly strange pre-recorded set of talks. I'll just wrap this up over the next 15-20 minutes, talking about machine learning and how we might be able to use it to solve some of the problems, multiple problems we face with site investigation projects. And then we can lead in, so Steve will lead some questions after that. So yeah, the title of this talk really was about kind of machine learning and is it actually useful. What I hope to do over the next few minutes is really to kind of showcase to you a couple of different ways in which I think it could be potentially useful, whilst at the same time providing some insights into why it might be useful and in particular how it might work, and therefore hopefully kind of giving people a bit of insight into how machine learning might be more broadly applied to the raft of different problems that we face in our site investigation projects. To try and make that topic a little bit more digestible, I've split the presentation down into 3 sections. So the first section really is going to be a really quick whistle-stop tour introduction to machine learning, and really just pitched in terms of why it might be useful and what are its features that might make it useful. I'm not going to get into the nitty-gritty of how machine learning works and what it specifically does. And then to try and help illustrate of some of the potential uses, I'm going to look at a couple of different case studies of it being applied to some of the problems that we face in a lot of site investigation projects. So the first of these is thinking about how do we plan our ground investigation locations to make sure we get the most out of them. And the second one is thinking about how we build integrated ground models and can we use machine learning to help link the geophysics and the geotechnical data. So we'll start at the beginning and we'll start thinking about what machine learning is. Like I say, it's not, I don't intend this to be a really in-depth discussion on machine learning and how it works and all the things it can do. I'm just going to give a very brief overview of what it can do really and the different ways you can pitch it, just to try and make sure everybody's kind of singing from the same hymn sheet sort of thing. So machine learning essentially is a field of computer science where the algorithm learns through experience. So perhaps the easiest way of illustrating this is with an example, and a kind of a classic case, a classic machine learning example you might see if you stick it into Google is training an algorithm where you give it a whole series of photographs of cats and dogs, and eventually you can train this machine learning algorithm so that it can then differentiate between what are photographs of cats and what are photographs of dogs. And so essentially what the algorithm is doing is as you're training it, it's learning to differentiate between the cats and dogs based on the attributes of those photographs. Now that's one really kind of simple basic case example of machine learning and what you can use it for, but there's a range of different ways in which you can kind of pitch learning algorithms and get them to work. So the one is classification. So basically kind of as I've just been talked about, that was essentially a classification problem where you would be asking the algorithm to say, is this a photograph of a cat or is this a photograph of a dog? A good example of that being applied to a marine site investigation style problem would be the example that I show with the image in the middle of the screen, which is a classification example from Lee et al. 2020, where they've trained a machine learning algorithm based on a whole series of bathymetry data, both morphology and backscatter, to then classify the seabed in terms of the seabed type. So that's sand, gravel, bedrock, etc. There are other ways, though, you can use machine learning. Sometimes, actually in quite a lot of cases, just simply binning data or binning your problem up is not really where you're wanting to go. So a second way that you can use machine learning algorithms are to solve kind of classical regression problems. So thereby, when you're taking one or more input parameters and you're wanting to be able to predict a secondary parameter based on that one or more input properties. So for instance, you might be wanting to take in, say, P-wave velocity and predict lithology. If you are doing a regression in that sort of sense, where you've only got one input parameter and you're wanting to try and predict just one output parameter, then that's relatively straightforward to solve with a classical regression approach. But where that sort of classical regression approaches tend to fall down is if you're trying to put multiple input parameters in. So what they call multi-attribute regression. So for instance, we might want to put in P-wave velocity, bulk density, and say Q factor, and from those try and predict what the lithology is of the subsurface. Now in that case, that problem is really difficult to solve in a classical regression framework. But you can get a machine learning algorithm to do that, and they perform extremely well with multi-attribute or multi-dimensional data. And in fact, they tend to produce more robust results if you're giving them more input parameters to work with. And the example I show up on the top right of the screen here is a regression example from Sauvant et al. 2019, where they were predicting CPT tip resistance using a range of geophysical inputs. The third way that you can kind of cast a machine learning algorithm to work that I think is useful for site investigation style problems is to use a learning algorithm to solve an optimization problem. So here you're saying that you have a set of input data and you're wanting to try and find the solution to that that is globally the most optimal solution. There's a range of different learning algorithms you can use to do that. The example I show in the bottom right of the screen is an application that I published a few years ago where we were using a genetic algorithm, which is just one form of learning algorithm, to essentially predict the acoustic impedance based on seismic trace input data. So just to kind of wrap this up, I think, machine learning algorithms have a number of strengths which I think make them really useful, or have the potential to be really useful to a range of site investigation problems. One of which is this flexibility. You can think about classification problems, regression, and optimization. The second one is the implicit ability to handle multidimensional data. And as we'll come onto as the talk goes on, one of the things that we tend to be good at in site investigation projects is getting lots of different data types. And if we can leverage all of those together, then I think it enables us to say a lot more about the subsurface in a much more kind of confident manner. So what I want to do over the rest of the talk then to kind of illustrate some potential ways in which machine learning could be useful to us are to take a couple of different case study examples. So the first one is then thinking about how we plan our ground investigation locations. This really comes about, I think, or becomes a problem because modern offshore infrastructure development sites are often very large. Typically particularly if you're thinking about offshore wind farm sites, you're looking at areas which are tens or hundreds of kilometers in scale. And increasingly, as Gareth has just shown for the Clare field, a lot of cases now we're thinking about trying to tackle geologically very complicated sites. The number of GI locations that we quite often, particularly for wind farm applications, the number of GI locations that you're wanting to try and plan can easily exceed 100, and so they come with very significant time and cost implications. So you really want to be able to get that right. So it's very challenging to try and decide where you want to place those GI locations to make sure that you get the appropriate balance between having a distribution that both captures the background variability or heterogeneity in the ground conditions, as well as also targeting specific structural or features that are particularly, that might be quite isolated, but are particularly interesting and might potentially be challenging. So, you know, trying to get that balance when you've got such a large area to work with, when you've got, you know, vast amounts, potentially vast amounts of, you know, hundreds, thousands of kilometers of seismic data, plus, you know, pre-feed GI data as well that you're working with. You're trying to balance all of that and come to a sensible decision from all of that can be really difficult to do, and it's incredibly complicated. As a result, I think often the fallback solution that tends to be used is to fall back on a fairly regular distribution that's either not or is only partially guided by the underlying geology. So a classic example might be along a cable route. You know, very often CPTs and cores are just regularly spaced along the cable route. There might be slight bunchings at particular changes where you can clearly see changing substrate, but in between those, you just fall back on a regular along track sampling. The same is the case for a lot of wind farm sites, where very often people will look at putting a CPT and or a borehole at every monopile location, just to make sure that you capture the ground conditions at those sites that you know you're wanting to put some infrastructure in place. There are obvious questions there about, is that the optimal use of resources? Are we getting enough? Are we therefore getting enough of a distribution and enough ground investigation sites to be able to capture the background spread in the ground conditions if for any reason we needed to move our infrastructure away from those pre-planned sites? Or equally, are we actually getting more GI locations than we need? So as our cost, are we getting so many that our cost benefit has basically already plateaued, and could we reduce that and save some of the costs? So, like I said, one of the reasons this is such a challenge is because we have quite a lot of data that we can leverage when we're trying to make those decisions. And as we've talked about previously, one of the benefits of machine learning is that you can give it lots of information, you can give it multiple attributes, and it will and it will work quite happily with those. So we can feed into the machine learning algorithm basically all the various bits of information that we can lay our hands on. So things like number and distribution of soil units, the stratigraphic and spatial variability in the seismic architecture, stratigraphic and spatial variability in the derived physical properties that we might get. You can also feed into it whatever information you have in terms of extant geological or geotechnical data. So you can essentially put all of that information in the pot and give it a good stir, and try and utilize all of that information to make a more informed decision. So the way we've been approaching that when we've been trialing this and looking to try and get some interesting results out is thinking about trying to parameterize a ground model in terms of a range of site-wide distributions of different properties. So for instance, what we're looking at, the images on this graph, on this slide here, are in the bottom left. If we're looking at the velocity distribution across this kind of subset of the site at one particular stratigraphic level. On the top right, what we're showing then is the distribution of that velocity, but at all stratigraphic levels combined together. So essentially, we're combining all of those different slices of the velocity distribution and presenting it as a global distribution for the site. What we then do is ask the learning algorithm to try and find a combination of locations across the site that best capture that site-wide distribution in the properties. And of course, we can do that for one property, so velocity, but we can also feed in multiple properties as well. So we can then, by being careful and thinking about what information we give it, we can then make sure that it's asking the right questions and that it's trying to capture that variability across the site. One of the really nice things we can do about this with this as well is that we can specify how many of those GI locations that it's trying to use to capture that site-wide distribution. So we can just trial it. We can say use 5, use 10, use 150, however many you want, and see how, as you vary those number of GI locations, you get how good how your essentially your fitness decays away or improves. So with that particular site, we feed the data in and we then ask the algorithm then to try and find a series of locations that best capture that spatial variability in those site-wide distributions. What we then can get out of that is a heat map of the potential GI locations. So what we're showing in the bottom here is a heat map where essentially red are the locations that are being highlighted as being areas where your the algorithm is suggesting is a better location to start to think about placing your GI sample. This case we ran it, just asked it to put 10 locations across that whole site. In the top right, what you can see is we're basically comparing how using those 10 locations has done in terms of predicting the velocity or capturing the velocity distribution. So in the background, we've got the gray histogram, which is the site-wide velocity distribution from the data, and the red line over the top is essentially presenting the same information, but based on the synthetic ground investigation data we would get just from those 10 locations. So it's not perfect. We'd never expect it to be perfect, but what we can see is it is doing a pretty good job at capturing that variability and the double peaked variability in the site-wide velocity distribution. I think, and we can vary this and pitch this in a number of different ways. So here we've essentially just given the algorithm free rein to test at whatever site it wants within the whole study area. But we can also very easily constrain it lots of different ways. So we could say, okay, well, it can only pick locations that are also coincident with seismic data. We can say limit it to only picking, only working with infrastructure locations, or we can also feed into that and say, well, we know we're going to put some GI locations at these fixed points, so we will fix those within the algorithm and then let it try and choose some other sites. So what I would say from this is that I don't think I would ever use this as a tool that says specifically, okay, go here, here, and here. But what I think it can be very useful for is essentially identifying areas where we might want to, as an interpreter, go back, look at again, and then think about in a more and use to make an informed set of decisions. So moving forward from that, I then want to look at the second example, which is then how machine learning might be useful when we're thinking about trying to build an integrated ground model. So this is coming back to something that I've spoken about a number of times previously, which is thinking about trying to leverage geophysical data and derive and form a better link between the geophysical and the geotechnical data. The point here really is we want to be able to leverage the high spatial density of the geophysical data to help us capture the spatial variability of the geotechnical properties. Now, we've plenty of people before me and myself previously have spoken about the complexity of the geophysical, of getting geotechnical characterization from geophysical data. One of the key problems is the parameters that we need to derive, things like undrained shear strength, relative density, etc., are not linked in a clear and straightforward manner to how the seismic wave field propagates. They are linked, but it's in a complex, interdependent, nonlinear manner. So it's not possible to directly invert those parameters from the geophysical data. Instead, what we tend to do, and the more robust way of doing it, is to invert the geophysical data in terms of properties that are more straightforwardly linked to the seismic data. So I'm showing a couple here on the slide in terms of Q factor and P wave velocity. And then what we can do is use machine learning to provide a bridge between those geophysical parameters and the geotechnical parameters that we really want. So just to illustrate that as a process, what I'm going to show is a case study, just talk quickly through a case study of that being applied to a commercial project. So this was a commercial project where we were de-risking some infrastructure maintenance. It's a site in the North Sea where there is a clay-rich layer underlying a denser sand layer, and the contractor, the client, wanted to bring in a jackup rig, but they were worried about punch through into that weaker clay-rich layer. So what they wanted to do is capture the spatial variability in thickness and the undrained shear strength of that clay-rich layer. They had quite a lot of extant GI from the site, but they were uncertain about interpolating that into the locations they were really interested in because of the spatial variability. So what we did is we used the seismic inversion and then machine learning to derive synthetic CPT profiles from hull-mounted pinger data at the specific spud-can locations for the specific jackup rig, both on its operational site and also to de-risk its standoff location as well. I'll quickly go through the next couple of slides and get to the results, because I appreciate I'm running a little bit on time. But we were, even though it was hull-mounted pinger data, we derived a range of different physical properties from the data. Probably the most useful at this particular site was Q factor, which enabled us to link the seismostratigraphy with the lithostratigraphy, because Q factor has such a strong response between drained and undrained soil behavior. We essentially could then use that to check that we were interpreting the right seismic reflections as being at the right lithostratigraphic boundaries between clay and sand dominated sediment. So not only did that enable us to check our interpretation was robust and we were picking the right reflections for the right boundaries, but also it enabled us to directly link the seismic properties in time with the lithostratigraphic properties in depth. With that as a basis, then we could use the machine learning to try and predict the CPT tip resistance based on those geophysical inputs, and we could do it in the depth domain. So what we were doing then was getting a geotechnical parameterization in the depth below sea floor. So everything essentially was in the right sort of space for design engineering. What we're looking at here are some validation tests that we carried out for the client. So this is 3 of those extant GI locations which we used as control points. So for each of these cases, the neural network which we were using to do this particular machine learning problem was trained using the other GI locations, and then we blindly predicted the ground conditions at these particular sites. The black line is the best prediction, the shaded grey line is the confidence interval associated with that, and the red line is the actual physical measured CPT tip resistance from that location that I reinforces that the algorithm hadn't seen when it was being trained. I think generally the take home from that is that the algorithm was performing really quite nicely. We got good tie between where you were going from sands to clays or clays to sands. The clay, the tip resistance in the clays was predicted extremely well. The tip resistance in the sands was predicted pretty well. There's some of the finer, thinner sand layers it wasn't picking up quite right, but given the complexity of those layers, I don't think that was necessarily much of a surprise. So the client was pretty happy with that. And so, like I say, what we could then do is generate synthetic CPTs at each of the spud can locations. And from that, derive undrained shear strength relative density as normal. The key bit, I think, for the client in this case, and has been in the case of a whole number of different projects, is that machine learning algorithms are by nature stochastic in their approach. So you don't just get a single estimate of what the conditions are at that particular site. you get a range of different estimates as well. So what we were able to do here was provide the client with essentially a probability distribution for the undrained shear strength for that clay layer, which then they could use and feed into their engineering design and de-risk the spud can penetration. I guess the take-home message from this is that, or the baseline is that, the jack-up rig got in, it did what it needed to do, and it got out perfectly safely. The measured spud can penetration depths were within errors of the predicted spud can penetration depths, and it saved the client somewhere in the region of about $10 million US, because they were able to use the jack-up rig that they wanted to, which was smaller and therefore quite a bit cheaper. So just to wrap this section up, though, what I would say is that there's lots of, one of the strengths of machine learning is, as I said back at the beginning, is it's very flexible. So in this case, we're pitching it as a regression problem where we're trying to take the geophysical parameters and derive a relationship that enables us to predict CPT tip resistance as a continuous parameter based on a set of continuous input geophysical parameters. You get into problems with that if you've then got a significant resolution disparity between your geophysical data and your geotechnical data. You can, to a certain extent, get around some of that if you then start to simplify the problem. So this is an example of some of the work we've been doing where we've been boiling it down actually into more of a classification problem, which if you've got slightly lower resolution data, you can use to then still get a pretty decent prediction in terms of the geotechnical soil characterizations. So just to kind of wrap this up very quickly and summarize so we can get on with the questions, what I've shown are kind of two examples of how machine learning, I think, can contribute to site investigations. We've shown how you can use it to systematically interrogate multiple data sets and provide some aid or guidance in where you might want to think about putting your GI locations to help capture the global background physical property variations, and also how you can use it in some ways to bridge the gap between some parameters we can maybe readily derive, so some of the geophysical parameters, and some of the parameters that we also might want than geotechnical parameters. But there are other similar cases where it might not be geophysical to geotechnical parameters, where you can, there are parameters you can get at, and there are other parameters that you want that machine learning similarly could be very useful. I think my take-home message, though, would be is that machine learning is not a golden bullet. I've shown some examples here where I think it can be useful, but it is dependent on the quality of the input data and the tractability of the problem. And I would echo, I think, what was a take-home from Gareth's talk, really, which was, you have to treat each site on its own merits. In Gareth's case, it was a very, very complicated site to try and work with, and so a lot of effort was put in, I believe, by that team in terms of thinking about what was the right tools to get the answers that they wanted at that particular site. And I would say that's very much the same if you want to try and use machine learning and get the most out of it from site investigation problems. You have to think about and treat each site on its individual merits. And I'll stop there. Thank you.
Great. Thanks very much. Thanks very much, Mark. That was fascinating stuff and a real sort of cutting edge aspect of the work we're doing. And the second one is from Gareth to Mark. He's talking about, Mark, your slide 3.3. Is the heat map depicting confidence in the ML-derived ground model, therefore instruct you where to focus your GI? Mark, I'm sure you can express that better than me, Gareth, if you just want to ask him directly.
That's okay. Yeah, it's basically the heat map you had on 3.3. To me, it looks like that's a confidence, I guess, map in how the machine learning has dealt with the data and found zones where it's generated uncertainty in its classification. Is that right?
No, no. So it's so the way that particular algorithm was run. So for that particular case, we were running it using a genetic algorithm to form to try and find the optimal locations with a given set of input and a given number of GI locations. And what we did then is essentially run that. So we essentially ran that optimization a whole raft of times, so 100 to 200 different optimization models. Each time the starting point, or the starting kind of combination of the GI locations, was randomly selected. So essentially what you're doing is you're doing an ensemble of optimizations and then looking for areas where each inversion kind of consistently comes back to the same location. So if it's consistently saying, okay, sticking a GI location here is helping us match that that global distribution, then it's kind of flagging up that, well, that location might well be a good location to physically put your GI in. So it is a heat mapping saying, these are the locations that the algorithm has kept coming back to and saying, these are, I guess, more representative or better at capturing that spatial variability. Okay. So, but that's what I think one of the reasons why I would strongly say is that I would see it as being a useful guide that helps potentially, that helps the interpreter get their head around what could be a huge amount of data and try and helps maybe focus different areas to look at and focus in on.
Thanks.
Right, Roy, do you want to put your question straight to Mark about machine learning as well?
I think you're muted, Roy.
Yeah, you're muted.
Yeah, sorry about that. Yeah, I think it was, I think Mark touched upon something similar in one of his last slides about the outputs coming from the machine learning exercise, if they can be quantified in terms of what's the uncertainty associated to the answer that machine learning provides. And I saw in one of your slides, you produce actually a quantitative value for how good the interpretation is. But I wonder, in terms of parameters, geotechnical parameters, for example, that I think was the last slide that you provided, where you provide a profile of shear strength for the jack-up. Could you as well quantify what is the likely accuracy of that profile, for example?
So that last slide that I showed, so that was essentially, that was a probability map. So the way the machine learning was cast in that particular sense is that was showing the probability that the soil at that location and at that particular depth had either that shear strength or relative density, that basically that soil strength classification. And so what if you look at that, basically quite often you had a kind of spreading of the classifications. So there were certain classifications that had hotter colors that were more likely, but it was also they were still warmish colors quite often in adjacent bins. And so within that, in that particular case, we were very careful on making sure that we pitched the machine learning algorithm in a way that it was giving us a probability. It was a fully probabilistic approach. So within that, you could then see, not only, we were very careful not to just give a single value. We were wanting to try and capture that potential distribution so that, it can be used. Because I know that, I mean, I must admit the geotechnics and the foundation design and stuff is still somewhat of a dark art to me, but I do know that you guys you're particularly keen on having an understanding of the limits, lower or upper bound, depending on what you're doing. So everything that we've been doing, and this is where machine learning I think fits really nicely, is it's very easy to pitch it in that sort of probabilistic way so that you can try and capture the upper and lower bound, not just a single value that is probably a single value I don't think is particularly useful.
Yeah. No, thanks for that.
Excellent. Thanks very much. Gareth, did you want to ask Mark your other question about inverting data? Muted again, sorry.
Now there's my turn now. Yeah, just a generic question, Mark, about you know, looking at the jack-up problem there. I mean, just how long did it actually take to run the process, the inversion, and generate the CPTs? And then are there any limitations on the data inputs from a geophysical perspective that need to be taken into consideration when inverting the data?
Yeah, I mean, so that's a really good question. The so that particular case study, when we did it, took a little while, which, because it was one of the first commercial projects we actually went through that whole process for, which is why it's now come around that I've got permissions to be able to use it. As you know, the delays and everything. I think if we were to do that sort of problem now, you would be talking a week to 2 weeks to go through, process the data, invert it, and generate the results. It's not the workflows now are in place to be able to do that. Obviously, as the areas get bigger, the more sites you want to work with, or potentially the more complicated the site. You know, if you increase the depth, you've got more stratigraphic units that you're worrying about capturing, then obviously that can become more challenging and take a bit longer. But it's the sort of problem, I would say, that in most cases it's not untractably long. In terms of the limitations on the seismic trace data, the key bit, I think, is that there needs to be careful thought about how the data is processed. So I think, you know, this, like exactly like you were talking about with the Clare Field stuff, you know, you need to be thinking carefully from the get-go, really, about how you're going to process it, and you're going to process it in a way that satisfies the physics. You know, because you're essentially to invert the data, you're assuming that the trace amplitudes are true amplitude. So you need to be approaching the processing correctly for that. In terms of the machine learning, I think the limitations really are it boils down to resolution, and, you know, is your seismic, how big is that disparity between your seismic data and your geotechnical data? Because if you have, you know, as you showed, if you have too big a disparity between the two, you just don't see anything in the seismic that captures that geotechnical layering. And no matter how smart algorithms you put together, if you don't actually have wiggles that are related to your layering, there's not a lot you can do.
That's right. Yeah. No. That's great. Thanks.
Okay, thanks very much. Right, let's open the floor up now if anybody else has any additional questions.
Not from me.
So all clear from Gareth. Anything from you, Roy?
No, from me, no.
No, okie doke. Mark, you got any for any of the other panelists?
No, just to say thank you to 2 very good talks.
Excellent.
Likewise.
Oh,
Thank you.
great. Okay, well, I think that should cover everything we need to go through this morning. So thank you, listeners, viewers, for tuning in to today's presentations, and we look forward to seeing you in the real world face to face when COVID is over and we're able to resume conferences and business as usual. So thanks very much from all of us on the panel.